Hey electricians, I wanted to quickly go over the last assignment that you guys did earlier this week, the one that's called switches in series and parallel circuits. You guys worked really hard on it, and for the most part, you got answers that worked, but a few of them were a little tricky and quite a few people got some of them wrong. So I wanted to make sure that we went over the correct answers so that you could see if you were one of the people who made a mistake and so that you could learn from that mistake and become a better electrician. So first off, challenge A. Most people did pretty well with challenge A. You were supposed to remember add a switch to the diagram to turn off, in this one, both lights. And so most of you realized that, if the current is flowing from the negative side of the battery around, and then it splits, goes into both of those lights, comes back together and goes back to the other side of the battery, that all you had to do to turn off both lights was add a switch somewhere in one of these main sides, either this side or this side, to interrupt the flow of electricity going either to the lights or from the lights to the battery. So you could have done either side, but I'm using a different color so you can really see my switch. Many of you chose to add a switch kind of like that. And then that way, if the switch was closed, the electricity would just keep flowing and then go to both lights and back to the battery. And if the switch were opened, then no electricity could flow and get even to the lights at all. So that was one of the answers to challenge A. I also wanted to clarify, I think something that I did not explain very clearly during this assignment was that your switch doesn't have to be something clever like a pencil or a cool twisty paper clip or something. All the switch has to be is a place for you to open and close the circuit. So open it and stop the flow of electrons, or close it to start the flow of electrons. So when you're building one of these little circuits, this is the one that's in this challenge, it's the parallel circuit right there, to test this idea of having a switch on the side, all I needed to do was somewhere on the side, I guess I drew mine on the negative side of the battery, was to have a place where I could connect or disconnect the circuit, which for me is just connecting or disconnecting the wire from that side of the battery. Did that successfully turn both lights off? Yep. If I connect it again, does it turn them both back on again? Yes. So that is a switch. A switch is just a place that can open and close the electrical current. I didn't have to design some cool fancy little switch like you guys did in your invention project last week. If you did, cool, you got more practice inventing switches. But to test a switch, you don't really need something that's practical. You just need to be able to see if opening and closing the circuit at that place succeeds in doing what you want it to do or not. So that's a switch in its most basic form, is just a place to close or open the flow of electric current. So there's the answer for challenge A. You could have done this switch either on this side or this side, as long as it interrupted the flow either going towards the lights, going towards both lights, or coming away from both lights. All right, here's challenge B. This one was a little tricky for many of you, so make sure you're looking at your sheet to see if you got this one right or wrong. And there's no shame in getting it wrong. I just want you to recognize that so that you can learn from it and become a better electrician. So challenge B asks you to put a switch somewhere into this circuit to turn off only one light. That means the other light was supposed to stay lit. And I think that wasn't very clear in the instructions on the paper, so some of you didn't understand that, and that's okay. But the idea is that one of these lights would stay lit and one of them would be turned on and off. So where could we put a switch that would stop the flow of electricity from getting to one of the lights, but still let the electricity get to the other light? If you put your switch into one of these wires, that's where it would be. So it could be either one, it could be either side of the light bulb, but your place to connect or disconnect needed to be in one of these smaller sections of wire. So that's where I'm going to draw my switch. Right there. That way, the electricity, the current, can still flow from the battery and keep flowing through this top light bulb and come back before going all the way back to the battery. So this light bulb is still totally connected to the whole circuit. It's basically in a simple circuit right now when the switch is open down here. Just one battery, one light bulb, back to the battery. And then when this switch gets closed, then the electricity can go through both the top and the bottom light bulb again and turn this one back on. But the top one is always on. So the point of this challenge was to figure out a switch that kept one of the light bulbs on and turned the other one on and off, on and off. All right, we're gonna do this one really quick because I think everyone figured this one out fairly comfortably. So this one, the challenge was in a series circuit where the electrical current goes through one light and then the other, was to design a switch into the diagram to open and close the circuit so that both lights went off and on when you use the switch. So most of you figured out that anywhere in this circuit, if you put a switch in it, it stops the flow of electricity from getting back to the battery. So it doesn't really matter. As long as you put it somewhere into this circuit, you will have interrupted the flow of electricity so that it can't complete the full circle. And if it can't complete the full circle, then the battery is not going to be pulling on it from the positive side, is not going to be attracting those electrons from the negative side. So anywhere you interrupt it is going to be fine for this one to turn both lights off and both lights on. Challenge D. Dun, da, da. Challenge D was definitely the trickiest. It was the trickiest for me to figure out before I even looked up the answer, and it was very tricky for most of you too. So you're not alone if challenge D was hard for you, or if you kind of thought it was maybe impossible, because there's a little bit of a trick to challenge D that you might not have thought of before. And I certainly didn't teach the direct answer yet. So unless you tried a few different ways and happened to stumble upon it, it's okay if you never found the answer to challenge D or if you got the answer wrong. But let's talk about what the right answer would be. So challenge D, they ask you to put a switch, put a place to open and close the circuit somewhere in this series circuit to turn one light bulb off, but leave the other one on. So what you need to think about is if you were electrical current, if you were little electrons zooming through, well, not really zooming since they're slowed down by these two resistors in a row in series, but if you were electrons going through, where would you need to turn so that you would avoid one of the lights, but still get back to the battery? So here's the trick for this one, is your switch needed to find a way to connect from between the lights to the other side of the circuit. And some of you who did figure this out eventually connected it down here, some of you connected it over here, but somehow it needed to skip the second light so that when the electrons were flowing through from the negative side, they went into this light and then skipped this one, and the switch made them go straight down here and then back to the battery. That way, if the switch is open, so if I opened the switch, like turned it so it wasn't touching across to that other wire, then the electrons would just treat this like a normal series circuit. They would just go from the negative side through this light bulb, then this light bulb, then all the way back to the battery. But if I close the switch and make it actually touch another wire across, then what the electrons would do is they'd be going joop, 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 joop. They'd go into this light bulb, and you might think to yourself, why wouldn't they just keep going into this light bulb? But this is where you have to get into the mindset of an electron. They don't really have minds as far as scientists know, but pretend with me for a second. So if you were an electron and you were right here in the circuit and you had the choice of either going to a resistor, a skinny, narrow little light bulb filament where there were already other electrons, you know, kind of just stuck there because they weren't moving very well there, or you could take a path that had no resistor and just got you nice, flowing quickly back to the battery. Which path would you take? I know some of you are being difficult and are saying, I would take the light bulb. But what the electrons would actually do is they take the path of least resistance. You might have heard that phrase before in a number of places in your life. It's true about electricity. The electrons are going to try to take the easiest path that will have the least resistance to get them back to the battery. So that means that the electrons, after they go through this light, are just going to take this shortcut that you've made with this new switch all the way back to the battery, and this light is not going to light up. I'll show you what I mean by that. Here is the series circuit that I built for Challenge D. You can see that the light bulbs are lit. They're just very, very faint and dim because it is a series circuit and it slows down the current so much. But in order to try this out, I need somewhere that I can connect the wires after the electrons go through the first light bulb, before they get to the other light bulb, and just kind of make that shortcut. So what that would look like on here is that I need to find the negative side of my battery. The electrons would be going through this light bulb. So I need to take this little bare wire section here and have it connect to somewhere after this light bulb. So I'm just going to bring this and down and connect it to this so that hopefully the electrons are going to take the shortcut and skip this one entirely. All right, so you see that they're both lit right now. And then I'm going to connect this one to here. And this light bulb went out. This one stayed on. This one even got brighter because now there's only one light to slow down the flow of the current. So this light stays on the whole time, whereas this one over here is on, and now it's off, on, off. So that is the trickiest challenge of the whole assignment. But hopefully you learned that electrons take the path of least resistance. So as long as you give them a different path that is faster, they're going to take that. That's why if I connected the wires from here to here, would either of the lights be on still? What would I have created? It's getting hotter. Yep, I created a short circuit. So even though the lights were still connected, if I make a new connection, that would be easier, would have less resistance for the electrons. They're going to take that and they're going to just skip those resistors entirely. So that's a place to watch out for short circuits, is you might think to yourself, oh, the lights are still connected. But if there's a easier path the electrons could take, if these are connected here, the electrons will take that path and start going too fast and creating the heat of a short circuit. So don't connect it here, but if you want to test this out for yourself for Challenge D, you make your series circuit, and then after the electrons have gone through one light, to slow them down a little bit, then make them skip the other one by connecting it after that.